Okay, polymorph selection is a process with tremendous industrial importance. We can think about, so there are a lot of model compounds that people have studied. So this one is studied by a group at Wisconsin, the Leon U. Goes by the name red, orange, yellow because the polymorphs have different colors. And they also, you can see, have different crystal growth habits. They're going to have different solubilities. So there are a lot of pharmacokinetic properties, basically, that will change as you change the different polymorphs that you have here. These kinds of things also happen in the context of biomineralization and various inorganic crystallization processes. You can see here, for example, this is the calcite polymorph of calcium carbonate. This is aragonite, and this is vaterite. So these things all have the same chemical composition. It's the same calcium carbonate structure at the molecular level, but it's packed differently into the crystal structures, and it gives you very different properties, very different crystal morphologies, and very different physical properties that here, different organisms have learned to use these things for different parts of their skeletons for all practical purposes. Okay, so this one, by the way, is a human gallstone, has vaterite in it. So, from the pharmaceutical side, organic molecules quite often show polymorphism, and a very famous case is ritonavir, an HIV drug that was being produced and sold by Abbott Pharmaceuticals when a second polymorph was discovered. It was discovered because the gel caps began to crystallize, despite being formulated in a way that made them stable towards crystallization of a known polymorph. They were unstable towards crystallization of another one. And this new polymorph was basically completely insoluble. Patients were not getting their proper dose. They had to pull the drug from the market. By the time it was all over, they had to reformulate the drug and build new facilities to formulate these drugs, and the drug became more expensive, and there was a class action lawsuit, and there's basically a lot of good reasons to understand your polymorphism when you are to thoroughly explore the polymorphism of a drug and to understand how to produce one polymorph reliably when you are preparing a drug for sale. So when most people think about polymorph selection, they'll tell you that it's governed by Oswalds' rule of stages. Oswalds' rule of stages says that you start with the metastable solution, and you first precipitate out a polymorph that is metastable, and then maybe you have a transformation that converts that metastable polymorph into a more stable polymorph. Okay, so these are the stages of nucleation according to Oswald's rule of stages, that you're going down hill in the sequence from metastable polymorphs to more stable polymorphs. And we know that this is actually not the correct story, because we can sprinkle a little bit of pixie dust into a solution and change which polymorph comes out, right? For example, a surfactant or salt or acid or something like that. And it doesn't take very much. You just slightly change the pH or the surface tension on those critical nuclei, and you can change which of the polymorphs you're going to make. And so Stronsky came along and he amended Oswald's rule. He said it must not be the bulk thermodynamics, which is, of course, not going to respond to those kinds of small changes, but rather it must be the free energy barriers that you have to go over during the nucleation process. And this was, I think, this is work with Stronsky and Tatomanov, a very famous paper from the 1930s, and so it's a very clever idea, right? So I mean, basically, he's describing a situation where you have a metastable basin. This is the molecules in solution. There are no large nuclei formed yet, and then you have a one channel the system can take, which goes through a free energy barrier leading to polymorph 2, or another channel that goes through a lower free energy barrier leading to polymorph 1, and Stronsky says that this one going through the lower free energy barrier is the one that's going to win. Now this, as of 2009, was completely a schematic, right? So nobody had ever actually computed a free energy landscape that looked like this. There are a number of reasons for that, but that's what we basically set out to try and do. And we were motivated by this very fascinating work that was done in 2007 by Eduardo Sanz and Don Frankel and Marjolaine Dijkstra and Chantal Valeriani. And what they're doing is performing forward flux sampling simulations using the spherical harmonic based milestone coordinate here. This is this NYLM nucleus size coordinate based on spherical harmonics. So it's not polymorph specific, and that's a key thing to remember throughout this talk, is that this coordinate does not distinguish between the two polymorphs. It allows you to generate both of them. And what they found was that when they ran forward flux sampling with a set of moves that resembled the natural Brownian dynamics, so this is a mixture of oppositely charged colloidal particles. When they ran this simulation algorithm with something that approximated the natural Brownian dynamics, they always got charge disordered FCC phases. When they turned around and ran the same algorithm but using a different set of dynamics, where they occasionally allowed positive and negative particles to switch places with each other, then what they always got was cesium chloride nuclei. Okay, so this is a nice piece of evidence here. You have two ergodic sets of dynamics. Both of them have rules that are completely consistent with detailed balance and approaching the same equilibrium distribution, and so they should have the exact same free energy landscape. But you see something quite to the contrary. So here you change the dynamics and you get two different polymorphs. So this means that the free energy barriers, as Stronsky told us, must not be the entire story. And somehow the dynamics are influencing polymorph selection here. So they put forth some explanations for how this could be happening, and their explanations are completely consistent with what they see in these simulations. But in explaining this, they assume that there were these two separate pathways as envisioned by Stronsky and Tatomanov. So you have these two separate pathways. One leads towards FCC, one leads towards cesium chloride, and presumably, based on some of their work, the cesium chloride one has a smaller free energy barrier. However, they had never actually separated these two free energy barriers, right? So their evidence in drawing this conclusion, based on the existence of these two different pathways and this so-called self-poisoning mechanism where the quasi-equilibrium assumption breaks down, is all coming from a projection where they take the dynamics and the free energy and they project it onto one coordinate, this NYLM coordinate. And that coordinate, remember, doesn't distinguish between which way you're going on the free energy landscape. So in short, this is sort of a caricature of what they're doing. This is the Stronsky-Tatomanov picture where you have one channel going one way in phase space and another channel going another way in phase space. And forward flux sampling is really driving the system to make progress along either of those two channels non-specifically, right? So in some cases, that's an advantage. And in the case of trying to understand polymorph selection, I'm going to argue that it's actually a disadvantage. So the reason it's a disadvantage is because you have an intrinsically two-dimensional process. You have to decide which of two pathways the system is going to take, and in order to understand why it takes one over the other, you're using a method that projects everything onto one dimension. So effectively, you've projected the answer to your question out of your simulation results, and that's a bit of an unfortunate thing, right? So you can see here that, of course, you can have some confusion from taking something that's intrinsically three-dimensional and projecting it onto two dimensions. It can sort of obscure the real picture of what's going on here. So if we want to understand polymorph selection, we have to use one coordinate per polymorph that can be made by the system. Okay, so this is really just formalization of this picture by Stronsky and Tatomanov, right? So if you got a metastable basin and you've got a polymorph 1 that lives out here, polymorph 2 that lives out here, in order to understand why I take this route to polymorph 2 versus polymorph 1, we have to have coordinates that will separate those two pathways in the free energy landscape. And so I'm going to show you how we can actually do this now. In order to do it, we have to have what I call polymorph specific nucleus size coordinates. Those should specifically distinguish between the different polymorphs that can be made. And they should still be local order parameters, right? So we're still sort of keeping these essential ingredients of the Tenwald-Frankel NYLM kind of coordinates here, but now we're introducing ways that we can actually distinguish between which atoms are in cesium chloride-like environments and which atoms are in FCC-like environments. And there are a lot of details that go into doing this. We're basically using a template strategy, a template matching strategy, to decide whether an atom is in a cesium chloride-like environment like this one, or whether it's in a hexagonally packed environment like the FCC phase. So once you have those coordinates, you can then use two-dimensional umbrella sampling kind of strategies. And this is the results of two-dimensional umbrella sampling, and it looks quite a bit different from that picture that I sketched as a caricature of the Stronsky-Tatamanov theory. Okay, so you do have the metastable basin down here. This is where nuclei of all types are still small. And then as what you expect is that as you start to grow an FCC nucleus, that you'll be moving along a channel going out here to the right. And as you start to move along the cesium chloride axis, you should have another channel going up here in the vertical direction. Instead, what you have is one channel that actually straddles the two. Okay, so this actually looks somewhat like the direction that the FFS simulations were pushing. And the other thing that's really bizarre here is that if you look near the saddle point in this one broad free energy channel, you see that the nuclei are actually sort of distorted versions that are kind of ambiguously structured, right? So I've got from one direction, I see a nucleus that looks like it's approximately cesium chloride ordered. And if I just rotate that nucleus around, I see a new vantage point now where it looks like it could be an FCC nucleus, okay, with a hexagonal packing. Okay, now the truth is that it's sort of imperfect on both structures. And it can tolerate that imperfection because it's still very small. Okay, so you can think about the distortion from the ideal structure is going to contribute an energy contribution to this nucleus formation. That if it continues to grow and it remains distorted, that is going to scale like the size of the nucleus. So obviously, at some point, the proper structure must lock in. But here, at small sizes, it's still possible for these things to be ambiguously structured halfway between these two polymorphs. Okay, but then that raises another question. If you have nuclei that are ambiguously structured here, and they're just sort of growing in size with some kind of order that's halfway between two kinds of things, why does this give rise to two different polymorphs? Okay, well remember that when they saw two different polymorphs in their system, they saw it because they changed the dynamics, right? So when you run the dynamics with no charge swaps, this is the approximately natural Brownian dynamics, you see that the system can move rather quickly along the FCC direction, but basically has no mobility moving in this vertical direction towards cesium chloride structures. Okay? When you add those charge swaps to the dynamics, now it's sort of easy to move back and forth going from charge disordered FCC. You can reorganize that nucleus at approximately constant size into a charge ordered nucleus of the cesium chloride type. Okay? So this change in the dynamics, I think, is actually what they're seeing. This is the eigenvalue scaled eigenvectors of the diffusion tensor. Okay, so how do you actually get these things? You generalize the Einstein relation, so you got 2 times the diffusion tensor times time is equal to a covariance matrix. And this covariance matrix represents little swarms of trajectories started at various points, the centers of these little crosses on the landscape, and I let them run just for a short moment here, right? Just long enough to see which directions they can move quickly and which directions they move very slowly, right? So this is a caricature, if you want, of the dynamics in the space of these two slow variables, nucleus size for polymorph 1 and nucleus size for polymorph 2. Okay? And once you've got that information, now I have a two-dimensional free energy landscape, the free energy landscape on which polymorph selection occurs, and I have the two-dimensional diffusion field for the diffusion tensors that govern the different directions of mobility and rates of mobility on this free energy landscape. And now we can build the Fokker-Planck equation, right? So this is the probability, the differential equation that governs the time evolution of the probability distribution. If you start here, what's the probability sometime later I will have escaped in this direction versus that direction, right? So this is what the Fokker-Planck equation allows us to do. And what's amazing here is that when you do that and you solve for the current lines, these current lines then are a reflection of the way the system is actually escaping at steady state, you actually see something that looks a lot like the forward flux sampling results. For example, with the natural Brownian dynamics, the system has enormous mobility along this bottom axis and very little in the vertical direction. And so the escape pathways tend to shoot below the saddle point and move preferentially off in this FCC direction. And that, I think, is really what the work of Eduardo Sanz saw in his study. So I think that this is actually quite exciting. I want to emphasize here that what we're doing is choosing the slow variables that are needed to understand the problem, building the Fokker-Planck equation by doing a rather inexpensive free energy calculation and an inexpensive calculation of these short little swarms to get the diffusion tensor. And then from that, you can actually understand the physical reason for what's happening in the system. So I think this is really a quite general framework for understanding polymorph selection. I'm quite excited about it because I think that there's no reason that we can't move on and do this for real molecules now and begin to make a real impact for things like pharmaceuticals. So I want to emphasize as well that this is a strategy for coarse graining. I will say that in the next slide in a little more detail. Let me first point out that similar things have been seen in molecular crystal nucleation. For example, this is D-mannitol crystallizing out of water. Actually, this is a seed that the authors have dropped into the solution. Before I tell you about what happens here, let me point out that the thermodynamic stability here is that D-mannitol forms two polymorphs. It forms alpha and beta. Beta is more stable than alpha, but alpha grows faster than beta. And you would expect, your intuition immediately tells you that if you give the system a beta seed, that's the thermodynamically stable polymorph, that beta seed will grow a beta crystal. But what happens instead is that it cross-nucleates alpha on the surface of the beta seed, and then alpha grows quite quickly and exhausts the supersaturation, and now you have to wait for a polymorph transition to take you from alpha to beta. Okay? So this is basically the same thing on a much larger scale as what's happening in these simulations, right? The system leaves the metastable basin, not because it's seeded, but because of a spontaneous fluctuation. It arrives somewhere in the vicinity of this saddle region, often a little bit below the saddle, and then it has two directions that it can go downhill. It now doesn't see a barrier ahead of it anymore. It can go downhill by going in this direction, and it can make fast progress doing that, but it leads to the unstable polymorph. Or it can make slow progress going downhill towards the thermodynamically stable polymorph of cesium chloride. Which direction does it take? It takes the direction that could go downhill right now. Why would it wait? There's no barrier. Okay? So this is basically a situation where the polymorph selection is being governed by the anisotropic mobility of the diffusion on this free energy landscape where polymorph selection is occurring. And I think that I want to point out, in fairness to some earlier authors, Bereskovsky and Zitzerman really formulated all of this Fokker-Planck language for understanding nucleation and even understanding saddle point avoidance in these two-component nucleation problems back in 1995. And what we're doing here is really just providing a simulation framework for connecting the properties of individual molecules, or in this case colloidal particles, to the quantities that are involved in their Fokker-Planck equations, right? So they have this Fokker-Planck equation, which is built from a free energy landscape and from a diffusion tensor. In order to know those things, though, you have to first identify the relevant slow variables, and we do a lot of work on that stuff in other contexts. So if you have those slow variables, this is, for example, nucleus size of type 1 and nucleus size of polymorph 2, then you can begin to build the two-dimensional free energy landscape, build the diffusion tensor. You have now a Fokker-Planck equation, and that Fokker-Planck equation includes both the free energy and the dynamics. And from that, you can predict the polymorph selection. Now, it's rather important, I think, that it includes both the free energy information and the dynamics. There are a lot of coarse graining strategies that perfectly preserve the free energy information in getting rid of other degrees of freedom. But they almost always lose the dynamical information. If you find the appropriate slow variables to describe your process first, then you can have both. You can keep the free energy information and the dynamical information, and you can really predict the long-term dynamics, which is what I think is a stated goal of a lot of the multi-scale frameworks. But really, Fokker and Planck had this figured out a long time ago. It's just the missing connection to what are the appropriate slow variables to describe the process that prevent us from doing it. And, in the case of polymorph selection, we need these polymorph-specific nucleus size coordinates. Once we have them, I think we can begin to make reliable predictions about whether polymorph selection is favoring one polymorph because of free energy considerations or because of mobility considerations. So I want to thank the NSF Career Program for supporting this work, and we also have support from the NSF and some support for Los Alamos. In particular, Los Alamos has been funding a project to try and generalize this to the nucleation of glycine and paracetamol. Of course, we welcome industry sponsors on this project. I think there's a lot of things that we could do that would really make a connection with things that people in industry care about here. For a review, see this work by Agarwal and Peters, Advances of Chemical Physics 2013. This particular project that I presented here is in Journal of Chemical Physics in 2009, and I am the author on that. There's no student on that work. And the group website, you can find more information about these things on the group website, which is given here.